The shift must go on, but it will also come to an end. But we're looking forward to the next shift. Okay. Yeah, so welcome to the last day of this conference. The first speaker is Professor Philippe Goldner. He's from Paris University in Paris. Very impressive career. I will not mention all the awards, but you have a silver medal from the CNRS and also an ERC Advanced grant. And today, Philippe will talk about rare isotope crystals for integrated quantum photonics. Philippe, the floor is yours.
Thank you, Andres, for your nice, kind introduction, and many thanks also to Jorge for the invitation to this wonderful conference. Congratulations for the excellent organization. I think it's a very successful conference. So yes, today I would like to talk about rare isotope crystals in the context of quantum technologies. So quantum technologies have the goal to overcome the limitation of classical systems by exploiting the particular properties of quantum systems. And so activities in this field are usually divided in three main blocks. So first of all, you have quantum sensing, and on this image here, you see a magnetometer, which is based on diamond. And this device is able to measure very small magnetic field at the atomic scale and can be used, for example, to measure nanoscale magnetic structures for spintronics. Second area is quantum communications, and here a big part of the activity is devoted to ensure that you can have highly secure transmissions, in the sense that if someone spies on the communication, it has to be detected, and this is guaranteed by the fundamental laws of quantum physics. This is quite mature technology. Here you see this box here, which is a component which you can buy and which is sold by a Swiss company. And this quantum network for secure transmissions are already deployed on small scales in different parts of the world. And finally, you have quantum computing. This is a especially hot topic. I'm sure you heard a lot about that. Especially last week, we had the announcement of the 2025 Nobel Prize in Physics, which was awarded to three researchers for pioneering work in quantum superconducting circuits. I'm proud to note that among the winners there is a Frenchman, Michel Devoret. And one application of these superconducting circuits is indeed quantum computers. So the machine we have right now, they have fairly small processing power. For specialized tasks, they can already make calculations much quicker, than classical computers. But in the future, I mean, these are very specialized tasks. In the future, we can hope to have larger machines, which will be able to tackle real-world problems, maybe help in discovering new drugs, new materials. So this is the situation right now. But let's have a look at the future. The future is in part related to an exciting idea of the quantum internet. So it is a worldwide network, similar to the internet we have now, but which will be able to link quantum systems. So you could imagine to have, at a very large scale, communication or connections between quantum sensors, between quantum computers. The links will also be quantum, and protocols, devices will be provided by quantum communications. But to reach this dream, this very large network, we need new platforms. For these new platforms, we want them to interface with light, because light is an excellent carrier of information. We probably already know that because you have an optical fiber at home. So it's very efficient for classical communication, but it's also very efficient for quantum information. So these platforms should interface with light, and we also want them to have a large processing power in terms of computing, but also in terms of transmission rate. And to achieve these goals, there are many ideas, of course, but one approach is to use optically active solids. And in this case, what are we talking about exactly? So what do we want from these optically active solids? So first of all, we need an optical transition, which is shown here on this scheme. So this optical transition is, of course, there to allow interfacing with light. We also want to have, for this transition, long quantum state lifetimes, which is noted by T2. This is a parameter which will come over and over in my talk. So we want long-lived quantum states because, of course, if we want to use this quantum state for processing, for storing, we need them to have a long lifetime. In addition to these optical transition, a very useful additional resource is the spin transitions. Because the spin transition usually have longer T2 than the optical ones. This is well known from NMR, for example, or EPR spectroscopy. So this is because the spins are usually more protected from perturbation from the environment. And so the quantum states in the spin transition can live longer. And these spin levels, because of this long T2 time, are very nice for storage or processing of quantum information. And so when we have such a system here with a combination of an optical transition and a spin transition, we have so-called optically addressable spins. So this is really an excellent tool for building quantum light atom spin interface. So the idea is that you can create quantum state along the optical transition and transfer this quantum state in the spin transition to processing storage, and then transfer back the quantum state to the optical level and then interface to light again, maybe produce a single photon which will carry this quantum information along a fiber network. So this is the first important point. The second point also is that not only you can interface with quantum light, but we can also use classical light, lasers, to manipulate, control, read out the spin transition or the spin states. There are different solids which can be used for that, color centers in diamond or silicon carbide and related materials. You have quantum dots, which are also very much investigated. But in our case, we would like to focus on rare stop crystals. As I'm sure many of you know, these elements, they have this particular property of the shielding of the 4f electrons by closed shells. And this translates into less perturbation from the environment on the optical transitions. And in the end, it's possible with rare stop crystals to observe very long coherence lifetime or quantum state lifetime. So very long T2 in the range up to milliseconds. However, be careful that this is only possible at very low temperatures, so typically below 3K. This is quite unique in the solid state. Rare stop crystals are the material in which you can observe the longest optical quantum state lifetime in any solid. And also, very nice feature of rare signs is they also have electron and or nuclear spin transitions. And so we can really realize this scheme. And in this case also, you can observe very long quantum state lifetime for this spin transition. And in the case of nuclear spins here, this T2 can reach up to several hours. So really a long time to do processing and storage. Okay, and so with this unique combination of good properties for optical and spin transitions, rare dot crystals are investigated for several applications. So first of all, you have demonstrations of single ion, single spin, readout, control, single photon sources, quantum memories for light. All these topics are related to quantum communication. Then you have also protocols and, let's say, initial demonstration of quantum sensing, especially to measure small forces. You also have specific schemes which have been developed for rare stop crystals for quantum processing, with the idea to have a large processing power, so taking advantage of the atomic scale of the quantum bit. so which would be a rare earth element. You also have development of hybrid quantum systems where one wants to combine properties of two different quantum centers. And finally, you have also the topic of quantum transduction. And here the idea is to convert single microwave photons into single optical photons. And this is quite important if one wants to interface with light the quantum computers based on superconducting qubits, which are among the most powerful we have right now, because these superconducting qubits, they operate in the microwave range, so they cannot directly communicate through optical fibers. So there is a need of quantum transducers, and rare stop crystals can do this with potentially very high efficiency, very high fidelity. Okay, so the most popular rare signs right now, which are investigated for these applications, are, let's say, cerium, praseodymium, neodymium. Praseodymium is a strong candidate. You have europium also, erbium, and ytterbium. They are usually doped into a variety of crystal systems. Here you have yttrium orthosilicate, yttrium vanadate, and so on. Silicon also is a very interesting platform, for example, for rare ion applied to quantum technologies. Okay, so recently a particular interest appeared about photonic integrated circuits for quantum technologies in relation with rare earth science. And so these circuits, they are, you have a scheme here. So imagine a silicon substrate on which you can fabricate waveguides, interferometers, optical resonators, and able to perform all sorts of manipulation on quantum light, single photons, for example. Then you add some systems to generate single photons at the entrance of the chip, and then you have detection here with single photon detectors. And so these chips, they offer, of course, a lot of advantages, a very small footprint. They have high energy efficiency. They can also be fabricated at a very large scale. So it's a very exciting prospect, of course. And one idea also is to provide additional functionalities that you cannot obtain with these kind of components. And Rose-Dop crystal could bring to these photonic integrated circuits, for example, quantum storage of light, quantum processing, single photon sources, because again, Rose-Dop crystal have these unique capabilities of combining long-lived optical quantum states and spin quantum states, and also optically control these nuclear or electron spins. So one idea to couple rare science to these integrated circuits is shown here. So imagine you have this chip with these waveguides or different structures. And then what we could do is simply try to position a rare stop crystal on top of this circuit, and by this way couple the rare science to these structures. So here you see a zoom on this. So for example, here we would have some optical resonators that could couple to the rare science. So we are interested in different platforms, for example, gallium indium phosphide. This material is nice because it has both transparency below 600 nanometers or above 600 nanometers towards the infrared. It has a large refractive index, which is nice to fabricate very small structures. And this could be readily coupled to rare science, such as erbium, of course, but also ytterbium. And so it has, let's say, a broad range of rare science that can be used together with this material. Of course, you have other possibilities: silicon, silicon nitride, lithium niobate, etc. So in our group, we develop materials toward these applications. We study bulk crystals, which can also be interfaced to these circuits in some ways. But let's say the main interest here would be nanostructure materials. So we are looking at nanoparticles in films, molecular crystals, but also as hybrid systems between centers in diamond and also rare earth ions. So in the rest of the talk, I would like to first focus on bulk crystals, because I would like to show you how far we can go with the properties of these materials. So the bulk crystals are are really the very best systems you can have right now. And then I will switch to molecular systems, which will be more easy to integrate into the photonic circuits. So let's start with an example of a Pell crystal. And here I would like to talk about a new system we very recently started to work on, which is ytterbium-171 in calcium tungstate. So of course, calcium tungstate is certainly not a new crystal. It's really a well-known host. But the importance here is the combination of this matrix with ytterbium-171. And as you will see, it really offers outstanding properties for quantum applications. So these materials, they are grown as bulk single crystals by the Shklovsky method. So we are pulling the crystal from the melt. Melting temperature is relatively low, 1,600 degrees C. And you see a bowl here we obtain in the laboratory. As you can see, it's a crystal you can obtain with a very high quality, no, let's say, bubbles, no fractures. It's really a very nice material. And we dope the material with ytterbium. The nominal concentration is 10 ppm, but because of segregation, I would have only 5 ppm really in the material. This was determined by EPR spectroscopy. Why such a low concentration? It's simply because we want to avoid, as much as we can, interactions between ytterbium ions. So of course, with 5 ppm, it's not so much, right? So you may wonder, but really, can you see anything in such a material at such low concentration, only 5 parts per million? Yeah, actually, yes. And if you, at low temperature, so here we are 50 milli-K, you record the absorption of the crystal. You see all these lines appearing on the main peak here. You see that the absorption is actually not so low. In a 1 centimeter long crystal, you would already absorb something like 80% of the light, even though the doping concentration is really low. And why is this? Well, of course, it's because the lines are extremely narrow. Here in this frequency scale, it's 170 megahertz, but maybe if you are not so familiar with these units, let's say, which are usually used in high resolution spectroscopy, this corresponds to 0.0005 nanometers. So it's really extremely narrow. And this is why we can still get significant absorption, even though we have not so many ions in the material. These line widths are among the narrowest observed in rare stop crystals. Many materials, they exhibit at least 10, maybe 20 times broader optical line widths here. So you notice that we have different lines here. This is due to the doping with ytterbium-171. So this particular isotope of ytterbium has electron spin of 1/2. This is simply because ytterbium is a paramagnetic ion, but you also have a nuclear spin of 1/2. And the interactions between this electron spin and the nuclear spin will cause this lifting of degeneracies, and so you end up with 3 level in the ground state and 3 level in the excited state. And this is why we see these different transition in absorption. Now, to understand a little bit better what is the structure, we turn to an experiment where we apply small magnetic fields on the crystal. And here what you see is that from the situation at 0 magnetic field, which I just showed you, when you apply a magnetic field, you start to see a fairly complicated magnetic or variations for the transition. So each vertical slice here on this graph is a spectrum as a function of magnetic field. So you see that different lines are appearing when you apply a magnetic field. Some degeneracies are lifted. But as you can see also on the right side, based on spin Hamiltonians, we can fairly well simulate these lines. So the one corresponding to ytterbium-171 are shown in this purple color here. The blue lines, they actually come from ytterbium-174. It's an impurity of the original material we used, which is isotopically enriched in ytterbium-171, but there are still 5% of ytterbium-174, and we also see the transition corresponding to this isotope. But of course, we are not interested in these properties. So from the simulation of these spectra under magnetic field, we can end up with the energy level structures that you can see here. So three levels in the ground state, 3 levels in the excited state at zero magnetic field. But now what is interesting is to see what happens if we have small magnetic field fluctuation around this B equals 0 condition. As you can see, some levels, they have here horizontal curve, right? Horizontal shape. And so this means that the energy of this level, for example, does not vary so much, or even does not vary at all at first order when you have small magnetic field fluctuation. So this is why you have this flat shape here. This is also true for this level. However, here it's not true. Here you can see that you have a linear dependence with the magnetic field. But again, for these two levels here, you also have this property that at first order magnetic field fluctuation have no effect on the energy of the level. And so if I take now a transition between this level and this level, this is now in the optical range, we have the properties that the transition itself now is insensitive to magnetic field fluctuations. And we also have the same property for this transition here, which is in the microwave domain. This is a spin transition. And so these kind of transitions are well known in atomic physics. They are called clock transitions because they are used in optical clocks, for example, or microwave clocks. In the rare earth community, we call that ZFOS transitions. So this is for zero first order Zeeman transitions. And why is it interesting to have transitions which are insensitive to magnetic field fluctuation? It's because you will have a very much reduced effect of magnetic noise in this case, because we have these flat curves here. And why are we concerned with magnetic noise? Because in the host, we have nuclear spins. They come from tungsten 183, which has also 1/2 nuclear spin, 14% abundance in natural compound. These spins will fluctuate even at low temperature, go up, go down, and this is causing magnetic noise, couples to the transition of the rare earth ion and cause perturbation to the quantum states, and ultimately can limit the lifetime of these quantum states. So if we have transitions which are insensitive to magnetic noise, we may gain significantly in quantum state lifetime. And this is true, again, for optical and spin transitions at the same time. So this is a big advantage of this system. So the next step, of course, was to determine what were the lifetimes of the optical quantum states. And for that, we first use a technique which is called optical pumping of spins. So it's shown here on a very simple scheme. So imagine we start from this situation where we have two spin levels here in the ground state, which are equally populated, and we have the optical excited state. Now we shine a laser on this transition 1, 3. When the ytterbium ions arrive here in the excited level, they can relax by spontaneous emission, either to level 2 or level 1. If they relax to level 1, they can simply be re-excited by the laser, and we start the cycle again. But if they end up in level 2, they may simply stay there for some time. So if we shine the laser long enough, and the lifetime of level 2 is long enough too, well, you end up with all ions in spin level 2, and this is what I call polarization of the spin, so that we have all spins in the same level. So this is what we could achieve in this ytterbium doped sample. So we start from this spectrum in blue here, correspond to the situation where the 3 ground state spin levels are equally populated. But if we apply laser at the right frequencies on the right transition, we can end up with this situation here where all spins are now in this level that we call 4G. And so starting from the blue spectrum, we now see that we have the red spectrum, which is completely different, and we only have two transitions now. You see on this one, the absorption has been increased a lot simply because we have more population in the starting level of the transition. And this is very useful for quantum application, because in many protocols you need to initialize spins. You cannot do anything really starting from equally populated spin levels. You need some initialization. And this is what we can do here by using this optical pumping technique. So as you can see, the other transitions are really nearly completely disappearing, meaning that the spin initialization in this case is over 99%. Another very interesting feature is that this situation where we have this strong spin polarization is going to last for a very long time. Of course, again, we are at extremely low temperatures, 50 milliK, but in this case, we can observe that the spin relaxation, so the thermalization, if you want, of this situation towards this situation will take a few hours, 3 to 6 hours at this temperature. And this is very nice because it simply needs that you don't need to refresh the polarization very often. You can simply do it once, and then this will last for a long time. Okay, now we turn to measurement of the quantum state lifetime. We use for that a technique which is called the photon echo. Very nice technique, which is relatively simple. We shine a first laser pulse on the system. This light is absorbed by ytterbium ions. This creates optical quantum states. They, after the pulse, they evolve freely during a delay tau. After this delay, we send a second pulse, which will reverse the time evolution of the quantum states. And so that after the same delay as we had between the first pulses, after the same delay, all ions, quantum states of all ions are back to the initial situation. And at this time, we will observe a collective emission of light, which is called the photon echo. The point here is that only the ions which have no perturbation from the first pulse to the echo emission can actually participate in this emission. And so if we increase the delay now between the pulses, you will see the intensity of the echo going down simply because we have more and more ions which have been perturbed. And from the rate of this decrease of the photon echo intensity, we can directly determine the quantum state lifetime. And so this is what we did here. You see the photon echo intensity as a function of the delay. Here we have simple exponential decays. And we have two situations. So if we do not do the polarization of the spins, we observe a value of 540 microseconds. But this value is significantly increasing if we do the polarization. And now we reach, in this particular experiment, we reach 720 microseconds. Why do we see this effect? It's simply because when we polarize the spins in the same level, we actually freeze their dynamics. So with the frozen dynamics, the noise which is produced by the spin is reduced, and so the perturbation to ytterbium transition is also reduced, and we see an increase of the lifetime of the quantum state. So we have a situation of a frozen bath. Another very interesting feature here is that the longer T2 we could measure in the system is 0.75 milliseconds. And this is nice because now we can compare that to the fluorescence decay of ytterbium in this material. And this fluorescence decay is 0.385 millisecond. And it means that we are in a situation where this quantum state lifetime is actually at the intrinsic limit of the material, which is given by twice the value of the excited state lifetime, which is called T1. So T2 is nearly equal to 2T1. And this is quite remarkable because there are very few rare stop crystals when you can observe this limit. It means that all other perturbations are very small. So the only thing which is actually really interacting with ytterbium-171 in calcium tungstate is in fact the interaction with the vacuum field, its spontaneous emission. And so we have really a system which is extremely, let's say, on the one hand, very quiet or very low perturbations. And the ion also is very well decoupled from the remaining perturbations. And so this is also something which is very important for quantum communication, because this has, let's say, it's a very nice property if you want to do single photon emission, for example. Okay, next, of course, we also wanted to see how the spin transition were behaving. So with the same technique, we were also able to look at the spin echo decays to determine the spin quantum state lifetime. We can do it that with all optical methods, because with the optical transition, we can drive the spin transitions. And here also we find a really nice result. So if we look at this particular transition, which is insensitive to magnetic noise, again, a very low temperature, we find a spin quantum state lifetime of 150 milliseconds. So this was obtained by freezing the spin in a particle level, so after optical pumping. So what does it mean, 150 milliseconds? Well, if we compare to other crystals, it's quite amazing, because another very popular host for ytterbium-171 that we studied before is yttrium orthosilicate, and in general, it's an excellent material for quantum applications based on rare earth science. But you see that in YSO doped with ytterbium-171, we could have only 10 milliseconds. So we gain a factor of 15. And if we now move to ytterbium vanadate, also with ytterbium-171, we have only 44 microseconds. So you can see that calcium tungstate is really an exceptional matrix for ytterbium-171. And this is essentially due to the fact that it's magnetically quiet. In YSO, you have the nuclear spin of yttrium. It's a 100% abundant isotope. So you have more magnetic noise than in calcium tungstate, where you have only 40% of tungsten atoms carry a nuclear spin. So here you reduce the magnetic noise. And for yttrium vanadate, it's the same. Also, including the fact that in yttrium vanadate, you have a lot of defects, impurities, and paramagnetic centers, which will create strong magnetic noise. Finally, for the spin properties, we also look at the line rates. Okay, and here also we found something which is really outstanding, which is that the transition has only a width of 5 kilohertz. And here also, if you compare this line width with what we measured in this compound, ytterbium-171, yttrium orthosilicate, now we have a decrease in the line width of a factor of 100. And this is really very significant improvement over that. What does it allows you to do when you have such narrow line width? Well, if you drive the spin transition, since it's very narrow, it turns out that you can drive it with a very high accuracy. And so this is very important if you want to implement manipulation of these quantum states, because of course, if you want to do something interesting with this quantum state, you need to be able to manipulate them with a very high accuracy, and having an extremely narrow line width is something that is very helpful for this kind of tasks. So to conclude on this part, application of ytterbium-171, you have many. First of all, quantum memories. So the quantum memory is a device which is able to store quantum light and also regenerate this stored quantum light on demand. It's used in this idea of quantum network. It is used as a synchronization tool. So it's something you really need in your network. And so with rare science, and especially ytterbium-171, you can obtain broadband long storage time quantum memory. And calcium tungstate in this respect is a very interesting candidate, let's say. Another topic which is also developed in several groups is single ion, single spin control in readout. This is also related to quantum communication, the ability to generate single photons. Of course, if you can detect a single ion, you can also of course, now see single photons. And this is important for quantum communication in some schemes, let's say, and also for processing, because for quantum processing, you also want to be able to manipulate individual centers. And so with ytterbium-171, this is something you can do in a quite nice way. And finally, you also have this microwave to optical transduction topic I mentioned in the beginning, which is also investigated with ytterbium-171. And in all these different applications, different topics, we really expect calcium tungstate doped with ytterbium-171 to be a particularly interesting material. Okay, so this was a few, let's say, slides on bulk crystals to show you how far we can go with these excellent materials. But let's now move to something which we think has more potential for integration, for coupling the rare earths to these integrated photonic circuits. A new platform we started to work on a few years ago, which is rare earth molecular crystals. So here, the motivation is based on single molecules, which are well-known quantum emitters. These single molecules have been around for a very long time. They are very bright emitters. They show optical line with a high quality, but they don't have spins in the ground state. And so this is a key ingredient which is missing for many applications. Of course, with molecular chemistry, you have a huge flexibility in materials compared to the more traditional inorganic crystals. And this is very interesting if you want to tune properties, for example. And also for integration, potentially, there's a lot of possibilities in nanophotonic or electronic devices. Here you see an example of a single molecule which is embedded in a polymer waveguide. And this is a kind of integration we could think about. On the spin side, these rare earth molecular systems, they have been investigated for quantum applications, single spin control and readout, but not optical readout. Electronic readout was already achieved some time ago. Quantum algorithms were also run on a small scale quantum computer based on these molecular systems. And the main selling argument for this system is as a strong potential for scalability, because you can have multi-center molecules, you can have molecular crystals, and again, at atomic scale, you can have one molecule as a quantum center, and then you can imagine to have in a small volume a large processing power. So starting from these results, these potentially very promising systems, we thought about, okay, but what happens to the optical transition? And after a few trials, we ended up with this particular molecule complex where you have the europium ion in the center and then you have 4 ligands around. This molecule was crystallized in a monoclinic structure and used as a powder, essentially. Okay, so here you have a picture of the crystallized structure. It is a layered structure. Note that the molecule itself, what I just showed, is a charge, so you have also a counter cation in the structure. Okay, so first we looked at europium photoluminescence. So here we changed dopant. We moved from ytterbium to europium. So europium photoluminescence at low temperature, nothing very special. The transition of europium of interest for looking at long-lived quantum states is the 5D07F0. In this particular compound, you see that it's very, very small. So this is really far from being ideal because, of course, with a weak transition, everything gets much more difficult. This weak emission, however, is the only one which can exhibit long-lived quantum state. All the other ones are too much perturbed by interactions with phonons. So we need to work with this one. The emission is very weak. We could benefit a lot with integrating these molecular systems into a micro or nano optical cavity, because then with the Purcell effect, we could enhance a lot the emission rate. But still, even with the molecule as it is, the crystals and a powder of these crystals, we were able to look at optical quantum state lifetime. So it's exactly the same experiment we use for ytterbium crystals. So again, photon echo decay, photon echo amplitude as a function of the delay between the laser pulses. Here, at 1.4 K, we were able to measure 10.5 microseconds. So this is quite interesting in the context of these molecular emitters, because first of all, we were quite surprised to see any photon echo in the system. I mean, the general consensus was that these materials were not really very useful for quantum applications. But, well, no. In fact, you can measure something. It's 10 microseconds. Actually, it can be up to 70 microseconds. So in some samples, we could see a long component of the echo decay, which was corresponding to 70 microseconds. And what about other molecular emitters? Well, now we have quantum state lifetime, which is 2 to 3 orders of magnitude longer than what you can have with other systems, single molecule, purely organic molecules, but also other complexes based on transition metal ions, for example, chromium-4, which also has been investigated. So here we have a quantum state lifetime, which is much, much longer. And this opens, of course, completely new possibilities for quantum communication, for quantum processing. We can do this optical spin addressing and so on. It's really a very important feature if you want to use these systems for quantum applications. Interesting question also is, okay, here we measure 70 microseconds. With ytterbium, we had more like 700 microseconds, and we were limited by the intrinsic lifetime of the excited state. Here, the excited state limit is 1 millisecond, so obviously 70 microseconds were very far from this limit. So what is exactly causing this extra perturbations to the transitions? And one way to look at that is to record the temperature dependence of not directly the quantum state lifetime, but what is called the homogeneous line width, which is simply inversely proportional to T2. So if we plot this homogeneous line width as a function of temperature, so what we see is that when we increase temperature, the homogeneous line width gets larger, broader, so it means that the quantum state lifetime gets shorter. But an interesting thing here is that the different contribution we can identify by a fit to a standard model is first an exponential variation in this region here, say above 5K. But if you zoom on this part here, you see a linear dependence here at low temperature, okay? And interestingly, these two contributions are related very likely to residual disorder in the crystals. And so first information we can get out of this dependence is that if we improve the way the crystals are made, the crystal quality of the materials, we may, let's say, decrease these contributions. And indeed, this is what we have first indication, let's say, that this is the case, that indeed with a better crystallization process, we can decrease this contribution related to disorder. Now there is also a term which seems very small on this scale, but actually it's not so small. This is more or less the 70 microseconds we measure. So how can we do better here? Well, we have a contribution which seems to be essentially temperature independent. And so to try to identify what is causing this perturbation, it's not completely clear at the moment, but we suspect electric noise. Because we saw already this contribution in rare earth nanocrystals, for example, and probably also magnetic noise because we have the nuclear spin of the protons in the structure. And this is likely also to perturb here the quantum state. And we believe also, it's not completely clear at the time, but we believe that these are the main contribution to this limitation to 70 microseconds. We also look at the spin properties. We could also do this spin optical pumping. Basically, we start from an initial absorption. Here we have a very small scale in frequency or wavelengths, if you like. So on this scale, the initial transmission is completely flat. If we shine lasers at 2 different frequencies, we start to have this very complicated spectrum. And this is due to the fact that europium has a nuclear spin, and by this optical pumping technique, we can also polarize these let's say, 3 levels into 1. So population is moved from here to here by this optical pumping technique. And here also we can have very large efficiency of polarization. Again, this is very important because without spin initialization, you can't really run any quantum protocol. So this works well. And very recently, we, in collaboration with colleagues in Germany at KIT, they were able to measure spin echo decay, so the quantum state lifetime of the spin transition. And here they found about 600 microseconds, which is very nice because it's comparable to a few inorganic materials, traditional crystals. So we are not very far from what we can see in these more traditional materials, traditional crystals, and this is also making the whole system very promising for applications. So the optical transition is not yet up to what we could get, but on the spin side, we start to have very good numbers. Okay, so this brings me to the end of my talk. Before summarizing, I would like to acknowledge people in the group, especially Diana Serrano, who is leading the molecular crystal development, Alexei Tiranov, who worked a lot on the turbine exponents, and also Karolina Waszkowska, she's a postdoc researcher working on ytterbium. Also would like to take the opportunity to mention the opening of a position in our group. It's a junior professor position. I think it's a quite attractive position in, let's say, at least in the context of the French system, which has a lot of advantages otherwise, of course. And it's a position on quantum nanophotonics. So basically, more or less what I told you today. Also would like to thank our collaborators and funding agency. Just would like to mention again that the ytterbium work is done in collaboration with Sylvain Berthenin in the south of France, and also André Pharaon at Caltech, whereas the molecular work is developed with David Hunger and Mario Rubin at KIT. And so, in summary, rare science in crystal, stable, well-controlled centers with unique optical and spin properties. Ytterbium 171 in calcium tungstate, outstanding optical and spin coherence times, very narrow spin line. It's a really nice system, at least in our view. Whereas molecular crystals, a new versatile platform for integrated quantum nanophotonics. Of course, many challenges remain. Couple these high performance rare earth materials to nanophotonic circuits. This is relatively complex because you also need to manage the photonic circuit part, the coupling, the synthesis of the rare earth materials. We want to have clearly a better understanding and control of the relation between the rare earth matrix and the rare earth and the matrix, and also go on with exploring current new application. So not only related to quantum communication and quantum processing directly, let's say, but we are also now interested in some more fundamental questions like quantum many-body physics. And I think these materials, they can offer new perspectives on these problems. Thank you very much.
Thank you, Philippe, for a beautiful and very clear talk, giving us a look in the future of the quantum information world.
Also very nicely, calcium tungstate compact. Calcium tungstate is the oldest phosphor discovered in 1896 used for X-ray photography. So it was nice to see that old material back in a new world. Other questions? Surprise, Vargas.
Keep here, person.
Philippe, beautiful talk. Thank you very much. Now, if I look at your experiment activating calcium tungstate with ytterbium-3, I mean, you have wonderful properties useful for quantum technology, but yet you have a host compound where you have some charge compensation going on. Is that actually an issue, or have you seen any indications in your experiments that ytterbium-3 going on the calcium-2 side, for instance, does cause problems that you still have to get rid of?
Yeah, thank you for this question. Yeah, indeed, this is important. So I would say first thing you see is that there is not only one side. So the side I'm talking about is the substitution of ytterbium-3 into the calcium side. And here the symmetry seems to be relatively close to the original one, S4. So we can, for example, the spectra with magnetic field, this is fairly consistent with this. So I would say we don't see a very big influence of the vacancies, for example, which have to be somewhere. But of course, we are working at very low concentrations. So up to now, we did not go for concentration greater than 20 ppm, you know. So, I mean, at these concentrations, I think you are not yet at the point where this problem is really important. So, yeah. Thank you.
Other questions? Good student of Mars.
Yeah, thank you so much. That's an amazing talk. I have a question regarding the spin states. How does the site symmetry where the ion is located and the phonon energy of the host, because you mentioned orthosilicates and the fluorides, determine the decay time of the spin state itself?
So you mean the spin relaxation time? Or?
Yes.
Yes. Okay. So the site symmetry has to do with how many hyperfine levels you will get. The degeneracy you have in the ground state and the excited state, these levels which vary linearly with the magnetic field, this is due to the high symmetry. So the S4 symmetry, basically. Then you have the question of relaxation. So here we are quite in a relatively good situation, right? Because we had zero magnetic field. So the direct process does not happen, right? And then you have the hyperfine interactions, which is not too large. So this is also giving a small contribution to the spin lattice relaxation. And then for the two phonon relaxation, Raman and Orbach, this is very small because we are at 50 milliK. So at these temperatures, you essentially have no phonon excitation, really important. And so this is why you have such long spin relaxation times.
Very nice talk, Philippe. Thank you. My question is the following. Do you see any advantage concerning the complexes if the complex is a single ion magnet, for instance?
Yeah, so this is something that has not been investigated yet, let's say. But yeah, there are pros and cons, of course, like many situations. So I would say the molecular magnet could work fine, but of course you have to be sure that you will have these spin-spin interactions which are strong. So you have to make sure that this is not causing, perturbations and so on. But then you can also imagine some new schemes because of this strong coupling at a very small scale. And so this could also bring some new possibilities, basically. So I talked about this quantum many-body physics. This may be one avenue which could be interesting in this case. Maybe also optical to microwave transaction. There could be some advantages, yes, indeed. Thank you.
That's Lucas.
I have a question regarding the first part of your talk. So what is the thermal stability of this spin polarization in the case of the bulk materials? So what is the maximum temperature at which you can still preserve this polarization of the spin in the bulk?
But yeah, so that's a good point. So basically, do we really need to work at 50 milliK? Right? Maybe this is perhaps the thing you have in mind. I don't know. Well, I would say if we increase temperature, of course, you activate phonons, and so typically the lifetime of the spin will decrease. But typically, I would say until 1K, we can still measure very good numbers. Above 1K, it starts to impact the coherence lifetime. Yeah, I think so. 1K is more or less the limit.
Okay, Philippe. So it's just a general question. You mentioned and also related to the comment on Andrews that materials are coming back, some materials. And in the introduction, you mentioned again lithium niobate. So lithium niobate disappeared from the community, but now it's appearing again. And can you explain us why is lithium niobate becoming so interesting again? Because
Yeah, no, I think lithium niobate is actually extremely interesting. A lot of work on that, and it's related to integrated photonics, in my view, because in lithium niobate you can get these nice structures with very low losses. You can make resonators, you can make waveguides with very high performance, and it's an electro-optic material, so you can also tune the properties by electric field, which is not the case with silicon, for example. So in this respect, it's very interesting. And of course, for rare science, it's even more potentially interesting because you can readily dope lithium niobate with rare earth science, right? The only problem is that lithium niobate is a host with a high nuclear moment density. So you have the spins of lithium and niobium, and this is causing a lot of magnetic noise. So I would say it's potentially the advantage of the fabrication technique, which have been really very well developed, could in some way, make it for the problem of the reduced quantum state lifetimes. But no, indeed, it's a very very interesting material, and it's investigated by several teams. I mean, we also did some experiments there. Yeah.
More questions? Max again.
Yes, if I may. So I was wondering, I don't really know. How do you achieve 50 milli-K, and how are you sure that at the site where you're measuring the spin, it's really 50 milli-K?
Yeah, so the 50 milli-K is achieved in what is called a dilution refrigerator. So it's, I would say, essentially, on the one hand, a big cryo generator like you may have, similar to what you have at 10K, but with more cooling power. So this initial system goes down to something like 3K. Then you can have circulation of helium at low pressure, which will get you to 1K. And then to go below that, you need to use helium-3 isotope. So it's a mixture of helium-4 and helium-3s. You have a phase separation, which allows you to go to these milli-K. I mean, it's honestly, in quantum technologies, it's a very common technique because a lot of systems, they work only at milli-K temperatures. And now the question of the temperature of the crystal is indeed a good one. So here I mentioned 50 milli-K. It's a temperature which we call the base temperature, on the holder. The crystal itself is probably at higher temperature. So the spin temperature is maybe potentially 100, maybe even more milli-K.
Wow, thank you so much.
I also have many questions. I say good talks raise many questions.
Yeah.
So, everyone, is this the first time that a T2 of 2 times T1 has been realized? Because I've seen many papers on Spangle, and it's always T2 is much faster than T1. Is this the first example where T2 is 2 times T1?
Yeah. So I don't want to make a really, wild claims, but I think at least it's very few examples. Maybe europium and the magnetic field can approach that, but at zero magnetic field for sure. Yeah.
They go into europium. There, of course, T2 was much shorter. That was at 1.4 Kelvin, was 70 microseconds. If the relation is linear, then the T2 at 50 millikelvin would also be 2 milliseconds, 2 times T1. Why did you not cool europium down to 50 millikelvin?
Yeah, so by coincidentally, certain times, over temperature 30 times,
Yeah.
70 microseconds, 2.1 milliseconds.
No, you're right. I mean, potentially this could improve the properties. Of course, all this is extrapolations. We should do the experiment. So one issue of doing the experiments at milli-K temperatures is that we are using powders. And powders are quite difficult to cool down and to ensure good thermal conductivity. So these milli-K systems are cold fingers, there is no gas. And so this is the main limitation we need to overcome if we want to explore this regime.
And then maybe a visionary question. This is all very nice, but for application at some point, you would pretty like to go above 72 Kelvin. Is there a possibility to realize that? Or do we always need liquid helium for quantum computing?
computer.
Yeah. So this is a question of someone who is really outside quantum technologies, because if you go to such talks, everyone is at milli-K temperature. There is no real system which can operate at room temperature, except for maybe for sensing. Sensing is okay. With NV centers in diamond, for example. But if you want to have superconducting circuits with high performance, if you have quantum emitters which are useful for quantum communication, all this is at low temperature. And I would say, if we take the example of the rare science, fundamentally it's simply because the electron-phonon coupling, which is small, but still, if you raise the temperature, you have these problems that electrons are very sensitive to electric field, of course. And so it's very difficult to, I'm not saying that it's impossible to go above 3K, but let's say 77K would be quite surprising. But who knows, it's still an open question, but at this stage, I would say not very likely.
So we have to be very careful with our helium.
Yeah, that's right. It's a big question. Yeah. Well, perhaps an anecdote is that helium-3 is essentially produced by nuclear warheads. So unfortunately, in this aspect, I think we still have some reserve. Yeah.
Yeah. Last question to anyone? If not, let's thank Philippe again for